In this lecture, we'll wrap up our discussion of graphs, and we're going to do so in the context of something known as a spanning tree. So what is a spanning tree? Well, first, I have to note, this is only defined for a undirected graph, so none of our edges can have arrows. And given such a graph, a spanning tree is a subgraph of G, that is a set of vertices and edges, where that set of vertices and edges T is connected, it's acyclic, and it includes all of the vertices. So if we consider this graph we have here on the right side of the screen, we can see that it is connected in the sense that there are no pieces that are disjoint from any others. It's acyclic, there's no cycles, and it includes every single one of the vertices. So those first two properties make it a tree, the fact that it's connected and acyclic, and the fact that it includes all the vertices means it is a spanning tree. Okay. Now what we're going to concern ourselves with in this lecture is finding the minimum spanning tree. And here by minimum, I mean you sum up the weights on all of the edges and you want to make that as small as possible. And so you could imagine maybe, for example, that each of these nodes is a building or a city, and each of these lines is a potential power line that could be laid between them, and our goal is to connect everybody up. So in this case, we don't care about having any redundant connections, we just want to make the absolute cheapest network, and so we'll try and avoid these long connections, but occasionally you can't help it. Okay. So here's some examples of some spanning trees, just to get a sense of what it's like on other types of graphs. Here is a spanning tree that is sort of degenerate. It's a long spindly spanning tree, but it's still a spanning tree. Here's one that's a little bushier. And when it comes to spanning trees, we actually don't care at all how bushy they are. And the only thing we're going to care about is the fact that they have a minimum total weight. So here's a question for you to make sure the definition makes sense. How many of these are spanning trees? And I'll give you guys a few seconds to think about that, and then I will answer. Okay. So hopefully you have determined that this is not a spanning tree because it is disconnected. This one's not a spanning tree because it has cycles. And this one is a spanning tree because it includes all the vertices and is a tree. All right, that's that.